did in this architecture is representation is quite front and center. Okay, basically you have to represent the state, represent how the world evolves, represent what your actions do, and that sort of makes a lot of sense given, and it matches quite well with what we'll be doing in the course. Okay, but just to be sort of complete, I also should point out that there are people in AI, depending on how you count, they sometimes are in certain subfields, they are majority, some certain subfields they are minority, who essentially think intelligence and representation don't have to be connected. Essentially, let's just do intelligence without representation. Let's do it already, the Nike style of AI. Okay? So the idea, of course, if you are taking a robotics course, oftentimes, you wind up hearing about something called a subsumption architecture, where essentially what they do is let the robot do something simple, and then it basically is called behavior-based robotics, where you're just basically writing sets of behaviors, layering sets of behaviors on top of simple behaviors. Okay, it's a different style of writing agents. Okay, it actually winds up being quite useful for robotics in some sense. For example, it has to be said that this kind of intelligent agent architecture tends to make you do things top down. Okay, because oftentimes you may not actually know how to do anything in the world or how to actually understand what is happening in the world at the signal level, and yet you're too busy focusing on how to represent the world and do very nice reasoning algorithms on top of it. So that could be sort of a kind of a critique that can be made of thinking of methods that consider representations upfront. It's not that everybody must do it, but that's a particular kind of critique that you can make, and it was that actually made Brooks, basically Bradley Brooks, who is sort of the kind of the new dad of robotics. He is basically the guy who made the Roomba. This is the company that made Roomba. He makes Baxter, he makes Sire, he makes all sorts of robots. And when in many years back, he basically sort of argued that, to heck with the representations. Let's just use world as its own representation. I don't need to represent the world. I can be Simon's ant. Remember Simon's ant that we talked about last class? No, I can be Simon's ant. I don't need to represent the world. Let the world represent itself. I'll just behave in it. Now the interesting question, of course, is it's almost a very different style of programming agents. There are disadvantages to it, advantages to it. Okay, I want to bring this up just so you know that if you were to take an introductory robotics course, you're more likely to hear this sort of behavior-based architectures than model-based architectures. Okay, and the model-based architectures is the one that we'll do in the course here, and it's important for us because we can actually talk about, once you have a model, you can think about what will happen to the world before actually acting in the world. Behavior-based representations are essentially just compute. You're writing, you're learning behaviors, you're learning, there is never any specific form of representation that you're keeping. The closest these two will come to, and I'll just sort of foreshadow it, is if you want to, those of you who are into robotics, when we look at reinforcement learning, we'll look at something called, basically one of the nice things in reinforcement learning is model-based versus model-free learning. Model-based learning actually learns the model of the world and then learns how to act in it. Model-free learning just learns what to do in the world without knowing what is happening in the world. Okay, now one of the nicest things is in reinforcement learning you realize that both of them are possible. It's just a difference in algorithm change. Okay, you can either learn the value function in the MDP terminology, model-based will learn value function, and model-free will learn Q function. It doesn't make any sense to you right now, okay? But when you get there in about 3-4 weeks, you will realize that when you start talking about model-free learning, you're coming close to subsumption style architectures. So I'm just trying to give that so that you have an idea as to alternative views of developing agents. And sometimes in the case of reinforcement learning, it actually becomes easy to think about. In some cases, it actually is better to go with model-free rather than model-based learning. We are obviously the most intelligent entities, right? We are the ones who know what's going on in the world, and we do both model-based and model-free learning. Okay, can any of you tell me the model-free learning that you did? No, model-free learning that you're still doing right now. Swimming, running, bicycling. Okay, imagine trying to think during swimming exactly what action you should be doing. Those are the swimmers at the bottom of the pool because they're sunk. Okay? Swimming, bicycling, the things that you don't know how to explain to people. Okay? I also like to think of, if I am a teacher, I should be in the business of what? Model-free or model-based learning? So you think I should be in the business of model-based?
Because if someone asks you why.
Who asks why? People just sleep through the class. No, so you're thinking model-based. What do you people think? Do you think I should be hoping for model-based? I mean, if I'm trying to decide whether to be a computer science teacher or a swimming instructor, computer science instructor or a swimming instructor, what do you think is the job that will survive? You already are taking MOOCs. Half the time you are not coming to the classes, you are listening to some 150,000 people class that is being, that's available on the internet. Do you see what I'm saying? So I have no job because somebody already taught this, and all you need to do is put the model into your head and you are ready. I would say I should be a swimming instructor. I haven't yet seen people learning swimming by watching videos. Those are again the people who sink like stones. Swimming, essentially, you have to take lessons. And the lessons almost is, they'll pretty much tell you, put your hand here at this point of time, that's it. Don't ask why. And if you ask swimming instructor, why am I doing this? You don't get to Olympics, let alone get to the other end of the pool. Okay? Why? Because we don't know how to explain certain things. Not everything is actually declarative in our own heads. We do certain things without knowing why we do. We do other things by knowing how we do it. And we do both sorts of tasks. Okay? So it is actually reasonable to both understand subsumption-based style architectures or the model-free reinforcement learning and model-based architectures, because we do both. And different cases they have, I still haven't seen people who have great models of swimming. Okay? But it's like saying I am doing high-level planning for, so on one hand, by the way, the one, you already heard way too many times the word plan in this course, right? Not just because I work in planning, but really, if you have a model, the most important thing is planning. Outside of this course, when do you hear of the word planning in general? Anytime general elections come along, like right now, people are always into plans. What's your plan? What's your plan for this? What's your plan for that? What is your plan for taking care of world poverty? What's your plan for improving my salary? It's all plans. Why don't we believe, a kind of a model-free learning scenario, saying, just elect me, everything will come fine. That's what one of the candidates is actually saying. Right? So you have a model-free presidential candidate and a model-based presidential candidate. Normally, we always have two model-based presidential candidates and we just decide which model is better for you. which plans are better for you. In now we are saying, there's one person says, it's like swimming. I'll just put me in charge, things will work out. Okay, another person is providing plans, you probably don't know. I mean, it's like, like the Jack Nicholson character. If I give you the plan, will you understand really? Do you really understand the plans that presidential candidates have of how to solve problems? As Churchill once said, in war, it's critical that you have plans. It's not important to follow them. It's important to have them. That's what happens in elections too. And so in essence, there are parts of our life where we expect model-based reasoning and we expect plans. When you don't have plans for swimming, because a plan tells you exactly what motion you will do at what time. You have no clue. You just basically are figuring out almost based on what's happening right there. You see what I'm saying? And both are important. And even in the case of swimming, it turns out that at the level of swimming from one part of the pool to the other part of the pool, you don't have a plan. But if you are part of like an Ironman or a decathlon or something, you need to have some kind of a plan as to how do you combine these lower level things together into winning the competition. So the model-free and model-based are basically interleaved in some cases. So I make a plan for how to go from here to China. I have made a plan because I'm going to China. But that plan doesn't yet tell me, I haven't figured out whether I'm going to put my left foot forward or the right foot forward when I go out, when the cab comes early in the morning on Wednesday. I haven't figured this out. And believe me, I'm not going to figure this out. It's not worth my time. I do both. Here's a question.
I was going to ask if there's like an architecture where you combine both of them. And
Yes, basically that's the thing. Model-free and model-based
so
can
you
be
can,
combined.
like in robots, you combine those types.
You can combine. But typically, you will see the work that's been done is in either model-based or model-free architecture separate. But you really do need to bring them together. Okay. Okay, so furthermore, now this I mentioned in a previous slide. So we are now actually kind of done with this, and I'm just going to talk a little about atomic proportional relational models once again, and then get into the second part. Okay. So I mentioned to you atomic propositional relational first order. First order is when I wrote that quantified formula and said when you compile it, it can become infinitely large. Okay. So this is just a little more, one single slide with a little more detail. So atomic representation, the states are indivisible. They're just basically, you say S1, S15, S19, they're just black box states. They are atomic states. Actions basically tell you, if you work on the state, what states would you get? Directly. Okay? So in fact, in the atomic models, actions are mappings from states to either states or sets of states. Okay? If it is a mapping from state to state, then the action is deterministic. If it's a mapping from state to a set of states, then the mapping is non-deterministic. If it's a mapping from state to a set of states and the distribution on them, it's stochastic. You see what I'm saying? Everything that we talked about can actually become much more concrete here right now. Okay? So we will be doing in atomic states will be indivisible, there is no internal structure, actions are mappings from states to either single states or sets of states, and then the focus of reasoning is on basically trying to go from a given state to some desirable states. So we will talk about search, which is A-star search and so on. We will also talk about Markov-Adation processes, which basically tries to optimize the expected reward, expected cumulative reward over a long period of time. Okay, and Markov-Adation processes are still atomic state representation. There too, the states are indivisible. The only difference is instead of action taking you from S1 to S2, it's taking you from S1 to a set of states. And you don't know which one will actually happen until you do the work. Okay, so that's atomic. Propositional typically means that the states are actually made of state variables that can take some values. It can take continuous variables or discrete variables. And so then the state itself is changed by changing one of the state variables. And so you have a better grasp on how to change the state, there's more structure to the state. The actions then will be thought in terms of their effects on each of the state variables, instead of just going from S1 to S2. So for example, typically in the factored models, the actions might say, here is an action, it says, this action A can only be done if V1 is true and V2 is false to begin with. And then it will make V5 true, V6 false. And imagine there is 10 variables, V1 to V10. So now I'm talking about this action on any state which is made up of V1 to V10. Okay? And this action can be done if in the current state V1 is true and V2 is false. And if the action is done, you know that the new state will have everything that it had before, but now V5 would be forcibly changed to true and V6 will be forcibly changed to false. If you don't like true false, you can say V1 is 3.5, V2 is greater than 7.9, and then V5 will be set to 9.7, V6 will be set to 8. That is a factored action. Okay, previously, so basically what that means is the actions now can be compactly represented. Okay, why is this compact compared to the state action, the atomic model? Because in the case of atomic model, each action can be represented as a matrix. Suppose there are, let's say, 1 million states. Okay, then I can talk of an S 1 million by 1 million matrix. And each action is just a matrix of this kind. If it's deterministic, then I will say, suppose if I do action A in S1, I will get, let's say, S17, and I'll put 0, 0, 0, 1, 0, 0. Okay, and similarly, if I do the same action in S25, let's say I will get to S10, then 0, 0, 1. That's an action. Now actions are matrices. If it's non-deterministic, I can say when I do it in S1, maybe I'll get here, or here, or here. If it is stochastic, I'll just make sure that all of these numbers are positive and add up to 1 in every row. Okay, so in atomic models, each action is a matrix. It's an S by S matrix. And if S is 1 million, then each action is a million by million matrix. Compared to that, this is a much more compact representation. Right? Okay? And to understand where the compactness comes from, if you see, these are all true-false variables. These are all Boolean variables. We want to meet and are all Boolean variables. How many different states can you write with 10 true-false variables? So the first variable can be either true or false, 2 possibilities. Second can again be true or false, so 2 possibilities, 2 times 2. Third can also be true or false, 2 times 2 times 2. So this is, now you see the pattern, it's 2 power 10. Okay, so with 10 variables, you are able to represent 2 power 10 states. With 64 variables, you will represent 2 power 64 states. That's a huge number. You do a log reduction in the size of the representation. That's why you go for factored models. Okay? Now, one of the nice things is states are made up of state variables that take on values, and so you can, those can be propositional variables which are true, false, can be multi-valued, it can be A, B, C, D are the values for each. They can be continuous. It's any real number. You can take any real number value. Okay? And then the kind of focus we'll be doing is search plus inference. One of the things that you can actually be doing is, in addition to search, you might be able to say that if this state variable is true and this state variable is false, then this other state variable cannot be false. For example, imagine I am talking about a simple blocks world where I have a bunch of blocks on the table. Okay, suppose I say on top of block, what is there? And that's the value of on top of A. So on top of A, let's say there is B. Okay, now if on top of A, B is there, then the variable is A clear. That cannot be true because it has something on top of it, so it can't be clear. So state variables can actually have correlations between them, and you may be able to figure out, seeing the values of some of the state variables, what would be the values of the other state variables. That's basically inference in a logical form. So those are the things that you will wind up doing if you have factored representations. And then you can go to relational, where you have objects and the relations between them, and you can also go to first order. Just to put this in perspective, I'll show you a simple example that might make a lot more of a concrete sense to you, because we'll talk about it in a minute again. So this is an 8-state vacuum cleaner problem that was there in the textbook. Okay, so you have, there's a vacuum cleaner, there are only 2 rooms. The 2 rooms may or may not have dirt. Each room may or may not have dirt, and the vacuum cleaner can be either of the rooms. Okay, so now how many states are there? So basically, each room, this room can have dirt or no dirt, 2 possibilities. This room can have dirt or no dirt, 2 possibilities. And the vacuum cleaner can be in the room 1 or room 2, 2 possibilities. There are 3 variables, each 2 possibilities, 8 different possibilities. If I ask you what are the black box states, these are the black box states. This is state 1, state 2, state 3, state 4, 5, 6, 7. There are 8 states. I can talk about my initial state here. I can say my goal state is either 7 or 8, presumably because you want both rooms to be clean and you don't really care where the robot winds up, the cleaner winds up being. In which case then, using this black box state representation, you will have to come up with what actions should the robot do. You know, the robot might be, the cleaner might be able to, for example, do go left, go right, and suck, which is suck the dirt. Those are the only actions it can do. And I have to come up with a sequence of actions that it will do such that by the end of that, the rooms will be clean. Right? We'll actually look at this as the first problem of search. So, atomic representation, this problem will be represented as 8 states, S1 to S8. Okay? And then each state is seen as indivisible. All states are 8 by 8 matrices. Okay? So, for example, if you are in this state and you do the suck action, what state would you be in? If you're in this state and you do the suck action, what numbered state would you be in?
5.
State 5. Right? And if you are in state 5 and you do the suck action, what state would you be in? Still in 5. Right? So I can write suck action to be an 8 by 8 matrix. In fact, you can write a little note to yourself to write the suck action as 8 by 8 matrix in terms of zeros and ones. That way you know for sure you understood what I just said. Okay, so each action is a 8 by 8 matrix, and now the other interesting thing is if I now just add one more vacuum cleaner, how many states will there be? It will be times 2 again, because the vacuum cleaner can be the room 1 or room 2. So instead of 8 states, it will become 16 states. You add one more, it will become 32 states, and so on. Right? Okay? And if you want to consider noisiness of the room, no. So forget about this. Okay. So you have, that's the atomic representation. The propositional representation, I will just make up 3 variables. Dirt in the left room, dirt in the right room, Roomba in the room. Those are the 3 variables. This will be true, false, this will be true, false, this will be left or right. So instead of 8 states, I only have 3 variables. In general, the number of variables will be logarithmic in the number of states. It's a huge reduction in terms of the amount that you have to write. Furthermore, if I throw in an extra robot, the representation increases by just one more variable. It doesn't increase, it doesn't double, it just increases by one more variable. Of course, the underlying state space did increase, doubled. Okay, it's not like when you are writing your programs in higher order language, assembly language part of your, the underlying processor says, hey, this guy is writing programs in higher order, let's write a very small assembly programs for him. No. You will write a 1-line program, it becomes 150 lines assembly language. It will always be that way. But would you rather write 150 lines, make mistakes, or write 1 line? You know, much more useful to write 1 line, and it's much more compact. That's what you would wind up doing. Okay? So actions now can just mention the kind of variables they affect. So I can write actions this way. It's no longer 8 by 8 matrix, it's just a simple algebraic representation of what actions, what variables they modify. Okay? So representation becomes compact, and then when you add a second Roomba, it only adds an extra variable. Okay? Then finally, relational would be essentially on top of it. You can start saying the world is made up of objects, Roomba, left room, right room, and dirt. Those are the objects, and you have relations such as in robot room, dirty room. Okay, now this relational thing can be compiled to propositional thing, because instead of putting, if I have in R1L, I can write that in R1L to be a single variable in dash R1 dash L. That will become a state variable. Then I'm in this part. Once I'm in this part, I can come to this part. Underneath it all, you can still come back to state representations, at least modulo that other functions that I talked about earlier, which can actually make the state representation, black box representation infinitely large. Okay, but in general, this atomic, propositional, and relational are, the point of them is that you are you're making the representations compact, but they also allow for more interesting kinds of reasoning in addition to just search. And this is why we'll first do atomic for the both state search as well as Markov agent processes. And then we'll start doing propositional, in which case you have to talk about the logic, the representations for which you do logic and problems. Okay, so finally, we get to just doing, as I said, I just want to do in the atomic representation. That means I have indivisible states, and I will look for deterministic actions. That means when I do an action in a state, it will take me to an exactly a given state, and I know what that state would be. And the goals are simple. That means I tell you what are the states that have the goal property. I just need to figure out what is my best action. In doing this, I'll also assume that the environments are static. That means when I'm thinking, the environment is not changing. So if you go back to our guy here, I'm going to look at the simplest possible scenario where I have basically, in fact, I can say that I have perfect sensing, although sensing doesn't matter because the environment is static and the actions are deterministic. If the environment is static and the actions are deterministic, it doesn't matter whether you have eyes or not. Can you people make sense of that? If you know what state you are starting from, and you know that when you do an action in a state, you know which state you will get to, you don't actually have to look. You can close your eyes and do those actions, and you will actually reach the goal state. So in fact, when you have a static environment with deterministic actions, observability becomes a moot point. I can either call it fully observable or not at all observable. It doesn't really matter. Okay, and the goals, I'll say the simplest goals, I'll say some states are good states. You just need to get to one of them. That's my problem. And what is the solution? Solution is still, what action do I do next? And the way I'll answer this for this class of problems is, since the world is not changing, I can close my eyes. I look at the world, I know what initial state I am in. I'll close my eyes and think, okay, I'm in state S1. I have these actions A1 to A10. And I'll do A1, and then I will get to this state. If I do A2, I'll get to this state. A3, I'll get to this state. If I'm in this state, I can do these actions and get to these states. I'll go like this, in this place, this is a goal state. Wow, I reached the goal state, so I can come back. This is my plan, so I'll do this as the first action, this as the second action, this as the third action. I'll still not open my eyes, I'll just do those actions. I'm done. Okay? That's what is problem-solving agent going to do. That is how you took something which is called intelligent agent and made it into just a search-based agent. Because it doesn't need to look. It's not that, it somehow lost any sensing. It doesn't need to look because it has a deterministic scenario. Okay, now actually just before going forward, I'll say the simplest thing I need to do to make me look is if my actions actually have multiple outcomes. When I do an action in state S1, I might get either S2 or S3. I don't know which one. So I need to look to see which one I get into. That will require actual sensing. That you'll see in a minute. Okay? So, I'm just going to do a single agent, dynamic, static, deterministic world, how to go from initial state to the goal state. Okay. Before I start talking about search, I will talk about. So again, look at this simple scenario with the robot, and the two rooms, and the only percepts that you get are whether I'm bumping into something, whether there is dirt, and whether I'm in the home state. Okay, so it turns out that in this you know exactly where you are with these percepts. So you may as well assume that the sensing is perfect. But as I said, if you are just doing deterministic actions, you don't even need to look where you're going. Okay. The goals, I'll assume that if you get to a state where both the rooms are clean, then you're done. Otherwise, you're done. And then the environment, of course, is those two rooms. Okay. Now let's play this game. Mostly what I'm going to spend time on is this problem. Okay, this is where we will be doing all these parts. But, so that problem essentially says I have 8 states. Remember, these are all atomic states. There is no state variables right now. These are all atomic states. There are 8 states. And I'll tell you what are my goal states here. 7 and 8 are the goal states. So irrespective of where I start from, I just need to find a sequence of actions that will get me to one of those states. Right?